we were in the discussion of how we can make an embedded system power efficient, more power efficient. So, but besides power, there are other efficiencies which we are interested in. One is it should be code size efficient, and it should be also runtime efficient. All right. Besides being energy efficient. Now, if I write down energy efficiency on the other side, it should also be energy efficient. Now, we have seen some measures of how to make it energy efficient by dynamic voltage scaling and dynamic power management and other measures, right, some parallelisms. Now, this parallelism will also make it runtime efficient, and the runtime efficiency will also make it energy efficient, because energy is an integral of power over time. Similarly, if we make there are independent reasons besides power, there are independent reasons of making an embedded software code size efficient. The reason is that if the code size is less, then we need less memory to store it, right. So, the area consequently will come down, but along with that, as the memory increases, the power also increases and more memory accesses will be required. And if we have a small piece of code lengthwise, then also it will run in less time. So, therefore, code size efficiency also has got a relationship with energy efficiency. Okay. Now, but when we look at this code size efficiency, that means if I have a huge say wide word length and I want to make some writings on that, then there will be obviously more number of switchings, because for each 1 to 0 there will be a switch. So, if I can make it narrow, that is also advantageous, and over the time if I make the size less, also this size is less, the number of words in a program that will be accessed, then also we will need less number of memory accesses. Each memory access consumes power, right, because I have to float the address on the address bus, get the data on the data bus, all those things will come into play. So, one of the techniques of code size efficiency is being shown here. It is a compression technique, how we can do the code compression. As is being shown here, we have got the processor which is sending the address and getting back the data from the memory. All right. Now, our objective is that we will have a compressor and decompressor which will send the address here, and the address will be compressed, the code will be compressed here, and when we get it, we will get it decompressed. All right. The best way of one example, one of the good examples of showing it is, so if I can keep the codes compressed, if I can compress the code, obviously my ROM size becomes less. As soon as my ROM size becomes less, my address width becomes less. All right. So, I can, but now if the microprocessor does not allow such compressions, then once I fetch the compressed code, then I have to decompress it and put it in the microprocessor itself. A very nice example of this is in the ARM instruction set, which I am repeatedly encouraging you to read, because it has got this very nice feature, that is the thumb mode of operation. Thumb mode of operation. Okay. In the thumb mode of operation, we actually work with a 16-bit instruction, whereas Normally, in a non-thumb or the expanded mode, ARM can work with a 32-bit instruction. Now, let us see that what is there in this 32-bit instruction. This is an example, okay? And in this 32-bit operation, here is the opcode part, all right. There is a minor opcode, let us not consider that for the time being. We have got an opcode part. Now, there is a provision of predicated execution. Let me write it down. Predicated execution. What is a predicate? A predicate is a sort of expressing a condition, all right. For example, it rains is a predicate, okay. It is hot is a predicate. So, some situation. Now, we can specify something like that if the condition if a particular condition holds, do this, right. Similarly, we will see that we will come back to this hash if later on, but so if some condition do this. So, here there is some condition, some predicates that if this predicate holds, then do this, all right. So, that is a conditional operation, conditional opcode. That feature is there in thumb, okay. Then you can have some minor opcode which is long, then you have got the registers from where source and destination and a large width of constant. Now, most of the time we do not need this. So, it has been seen that mostly we can manage with just the major opcode and a smaller minor opcode maybe. Consider this major minor, do not go into the separation, say an opcode. Therefore, the opcode field becomes much less, and here I am coming with a reduced instruction set, all right, and the source and destinations are fine, then but the constants are much reduced. The constant, we need not deal with such big constants, thereby we can have 16-bit thumb instruction. For example, add to some register some constant, okay. Now, if we are lucky, then for a particular task we may be able to have all these instructions compressed to 16-bit instructions. In that case, we would get 50% reduction of space. In actual practice, it has been found that we can have around 65 to 70% of original code size, okay. Now, another point is ARM performance with 8 to 16-bit memory, if I consider smaller memory, is around 130%, it goes up, whereas with 32-bit larger memory it is less. Therefore, if I can now the compiler can produce the codes in this thumb mode. In ARM, as you study ARM, you will see that there are ways of setting the mode to the thumb mode or the normal mode. If you have it in the thumb mode, then it will take 16-bit instructions. You can also switch from the thumb mode to the extended mode. So, thereby using this I can reduce the size of the memory and the code size will be made more efficient.
How is the predicate decided?
That is by the, when you write the program, you will have to have those conditions given, or the compiler can also do that. We will show that later, that just like a compiler directives that we do in hash define or all those in C, there are hash if statements that you can add. Okay. So, but later on it has been found that it is not very much encouraged, because too much usage of such predicated statements does not lead to good readability. Okay. So, a number of, besides ARM, the same approach has been taken up by other processors like LSI, TinyRISC and all those. And it requires, in order to do that, it requires the support of the compiler and the assembler. Okay. Another very interesting approach is the dictionary approach. See, there are, I mean, if I consider a particular piece of code here, a particular piece of code, and let me represent the bit strings in this code, the bit strings in this code by some alphabets. So, A is a bit string, say. Okay. So, my program is like A, B, each of them are bit strings. All right, C, D, but I will not have distinct instructions all through. There may be that this same instruction has again at the machine level has appeared here, B has appeared here, right, and maybe again A has appeared here, maybe C has appeared here. In that way there can be repetitions, and maybe another instruction E has appeared here and A has appeared here. Therefore, actually I have got here, I can see that my code size is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 words, say, right. But actually I have got only A, B, C, D and E, 5 words, 5 distinct words distributed all over, right. So, if I have just the addresses of the distinct, so I have got 10, right, and say I have I store the only this 5 in my memory, A, which is quite wide, B, C, D and E. These are the instructions that are there generated by the compiler, but my sequence will be nothing but the addresses to these 5. So, how many bits do I need here? Only 3 bits. So, with a 3-bit width in this example, 3-bit width and 10 such scenarios, I can have access any one of those. So, essentially my program is a combination of these two, where I have made a reduction in this and here also I have made a reduction here. Okay. So, this is an encoding sort of, this is the dictionary. Okay. So, if I just do some calculation here, suppose I can also show it in the form of this slide, say here, all right. So, what is happening here for D bit instructions? I have got D bits coming to the CPU, all right. Ultimately, because of this, any of these instructions, any of these instructions will be executed, right, and they are quite wide, they are d bits, all right. Now, as I come to these d bits, but here what I have is my dictionary, where I have got b bits, just like here I had 3 bits and the depth was 10. So, here also I have got a addresses, a instructions, each of 3 bits. So, why is it b bits? B bit is actually producing the address to this. So, this I have got a table of already used instructions, the instructions that have been used. So, actually this is d bit, this is my what was this, all right. So, sorry, what happens is we get the b bits here, which is much less than d bits, and that serves as an address, and that instruction from here is chosen and fed to the CPU. Is it clear? I have got some instruction. That instruction is, say, this instruction. Again, let us come here. Suppose I want to have the first instruction A. That means I am generating the address, say 001 or 000. So, 000 here is pointing to this address, and this address has got d bits. So, this one is going to the CPU, right. Next instruction may be again say 001. So, this one will go, and that this instruction will be fed to the CPU. Okay. Therefore, what is happening is, if you look at this, uncompressed storage of d bit wide instruction would have required a number of instructions were there, like here this is the total number of instructions. So, if I had stored all of them together, the number of bits I require is a into d, a number into d width, right. In compressed code, each instruction pattern is stored only once. Therefore, actually I am needing a times b, so much space, and c times d, because these are being stored only once. So, c times d. Therefore, we hope that a times b plus c times b, c times d, a times b plus c times d would be much less than a times d. Thereby, we can get the compression. That is a very nice way, and this is used in Motorola 68000 and is called nano programming. Okay.
We can also use source coding for this.
I will come to that later. So, with this, now next we move to some other forms of. So, these are the two approaches that we have talked about for code size efficiency. Now, we will be talking about runtime efficiency. Now, in runtime efficiency, let us take for example, the digital signal processing application, the DSP applications. Okay. Now, you know this figure is very familiar to us. This figure is familiar to us, we have encountered that a number of times. So, we get a signal ET, we do the anti-aliasing, do sample and hold, and that signal is converted A to D and it is processed. Now, we are concerned about this processing today. We have already discussed about all these phases earlier. So, regarding processing, we are getting some input from the A to D converter. And typically, we get a signal, we want to generate a signal at a particular time, say at sampling point is T s. At T s point I have got some value. Okay. At this T s I have got some value, and I want to find the value, actual value, I mean x s for that. And how do we compute that? We compute this at this point by one operation. One very common operation in filtering is we take all the earlier values of this sample of this variable and multiply that with some coefficient. So, it is a multiply and accumulate. What do I multiply? I multiply a coefficient, current coefficient, with the values, the W values, these values which are coming from the A to D converter for k equal to 0 to k n minus 1. So, I am going back all the previous samples I am taking and I am making a multiply and add with respect to that, right. Now, as I do this, we do this using a digital signal processor. So, here we see a typical digital signal processor, which is ADSP 2100. Now, let us look at this piece of code very carefully, what we are trying to do. Before that, let me quickly come to this architecture of this DSP chip. We have got registers MX, MY are registers. We have got MR as another register, MF as another register. On the other side, we have got AX and AY, and there are two arrays A and W in these two memories, because here we are having the W values all stored in an array and the coefficients are stored in another array, right. So, these two arrays are already stored in the memory. We have got an address generation unit, this is very important, we will come to this a little later, where the address is being generated from this unit. Okay. There are some address registers. Now, let us look at what we are doing. Again, every time look at this. First of all, keep in mind that we want to achieve runtime efficiency. And what do we want to achieve? We want to achieve this, right. So, let us start from this point. In the register MX, I am putting the from the W array, which is here, the current element, the Sth element, all right. We are starting with that, and in Y we put from the array A the first element, we start with that. Sth element means what here? The last one that we have got, right. Now, we do in a loop. Now, this is the initialization, let us start with this, we did this and then we do MR gets MR plus MX time MY. So, what is there in MY? A0, and what is there in MX? WS. So, A0 WS minus 0, okay. K is starting from 0. So, I am taking WS, fine. Then and I am adding it to MR. Then this MX is getting the next, the earlier value will get from some address register A2 WS minus 1. Now, look at this address registers A1 and A2 are separate, okay, here, they are here in this address bank, address register bank, right. And then I increment A1 and decrement A2, clear. So, there are two arrays, all of you are clear about this. I have got two arrays, one is from W and one is for A, and W I am going this way and A I am going this way, right. So, and I initialize this sum, this is an adder, and what is this? This is an adder also, this is an adder, this is a multiplier, sorry, this is a multiplier and this is an adder. So, all these are hardwired, so that the multiplication and this addition, this multiplication is being taking place here and this addition are taking place in the same cycle. Okay. We are given a instruction, MAC instruction, multiply accumulate. So, we are getting this and the current result is in MR. Okay. Now, consequently what is happening? So, and we are decrementing this. Now, look at the initialization. So, all these things are being done as if in a pipeline, right, and we are initializing this pipeline by making this initial sum to be 0, A1 to be 1, because I am starting with A0, A1 to be 0 and then coming back here. So, then 1 is there and this is S minus 1, I started already with S. So, this thing goes on and it ultimately I get the sum here. So, this entire, now the point to stress is this, I want to have, since look at this architecture, the entire thing, forget about this A1 plus plus and A2 minus minus for the time being, let us not consider that. Besides that, all the other things in this loop can be done in one cycle, because there are parallel paths coming here and this entire operation is being done in one cycle. So, from here to here I can get the entire thing done in one cycle. Okay. All these things are taking place parallelly. This Mx getting WA2 is coming to this path while this multiplication is going on. Okay. So, but this address now I am saying, I will show how later, that while this computation is being done for the current values of A's, A1 and A2, parallelly the A1 and A2 are being modified parallelly in the same cycle, because I have got a separate address generation unit. Now, therefore, this was actually, if I write in this ELO box, this was my entire loop, entire body of the loop, this entire thing, initialization chhod do. Leaving aside the initialization, if I look at this part is all in this, right. This part I will come in a moment. Now, all these things can be done at the same time, because I have got parallel paths. I can do this multiplication, I can do this. So, this entire thing can be done in one cycle. Now, the question arises, so what? I have got to carry out this loop, and for that I have to check for this condition. Now, for that again special hardware arrangements or special instructions, it can be done in two different ways. This part is handled, this looping is handled by a thing called zero overhead loop. Zero overhead loop. What happens is, for the, what do we do usually in our C programming? What did you do? We carry out a body of the code and then go and check the loop. Now, in zero overhead loop, what we do, while the body of the code is being executed, parallelly the loop condition is being checked, that whether the loop condition will be executed. Now, here again I can refer to the predicated scenario. I can make this whole body to appear as something like Suppose I do in this way. Now, if this one is carried out parallelly along with the loop, the earlier iteration of the loop, and I am checking this parallelly, then I am not spending any extra time for this comparison. Now, this can be done in hardware or this can be done using instruction prefix or by instruction prefix. So, this is an instruction and I am prefixing that. So, this is a very, these are some very important novelties that came into the embedded processing in order to add to the runtime efficiency. Okay. So, now, the point that I have not yet addressed is this: how is it the address is being generated parallelly? For that, if I go back here, I am showing this address generation unit, right. The address generation unit is being shown here. So, this address generation unit is in this way. Let me show this first in this form. Let us look at this. This is the address generation unit where I have got the address registers. It may be 4, 5. What does it mean? That 4 or 5 different arrays I can, these address generation registers are actually serving as the indices, the index of the register array. All right. There is an array. I will store all arrays. Array is a very important component of any DSP processing, and we will see later that we do not want linked lists to be used there. So, I have got an array. So, it may be W1, W2, where there are and say this is an array W, this is an array S. All I am showing of the same size, but it may be another array of smaller size also. Suppose this is S, this is M. There are 3 different arrays, and I am doing some operation with the indices here, what we call say I, J, K. For each of these indices, I am having an address register. Maybe A0 is pointing to this, A1 is pointing to this, A2 is pointing to this. Now, when I carry out the operation, suppose I am taking this element and multiplying with this element and maybe storing in this element. Okay. Suppose. Now, I have to, after that I have to increment all of them, A0 plus plus, A1 plus plus, A2 plus plus, that is taking time. Now, address generation unit, what it will do, along with this operation, it will either increment and or decrement these indices, so that that is automatically done. How is that done? So, this operation is, now it will be clear. I have got this A0, A1s here. They are pointing to the data memory. Data memory are these wherever these arrays are. Okay. And I have got an adder with a multiplexer. So, I have got already got a 1 fed. I will have some control for plus or minus, auto increment or auto decrement, and I can, along with the instruction, I can increment this. While the instruction is being fetched, the instruction is either A1 plus plus or maybe 1 plus M. If it be A1 plus M, then I will have some modified registers. You mean, do you understand? No. I mean, I can increment it by 1, auto increment, or I can shift it with an with a offset, right. So, what would be that offset value? That can come from a memory register, memory register that I add with A0 or whatever, some value x. So, that is coming in from the register. So, either I can, depending on the instruction, I can either select this or I select 1, all right. Whatever is coming, I add either of them, and that is coming to this point, and it is automatically added. And so, it takes effectively 0 time. If this can be done in parallel with the main data path. Main data path was where I was doing that loop thing. A plus minus 1 also takes 0 time, A plus minus m also takes 0 time, right, and it minimizes the load immediates. Load immediates I need not, that is automatically coming. So, that is a nice way of optimizing this. So, just summarizing, the DSP processors are specially tuned for such runtime efficiencies, not that others are not tuned, but I am just showing how DSP processors are tuned, that is using this address generation registers and also with heterogeneous registers. All these registers are not doing the same function. Here is an operational unit which is doing multiply accumulate in the same cycle. Okay. So, that altogether allows us to have a very faster operation. Now, we will break for a while and